All right. Assalamualaikum once again, and a very good afternoon. First and foremost, welcome to this month's Photonics lecture series.
그렇게 되면
Oh,
남겨진 넌 어떻게 살까?
okay. Someone else is.
Unmute, Min.
Oh,
계속
mute. Sorry. Oh, I was muted. Sorry. Okay. So again, assalamualaikum and a very good morning. A very good afternoon. Thank you once again for joining us this afternoon. Today, we will be having a very special guest, which is Dr. Fatin Hamimi Mustafa from Inform University Science Malaysia. And she will be talking about a low-cost near-infrared device to monitor nutritional status of newborn infants. A little bit about Dr. Fatin Hamimi. Dr. Fatin completed her PhD in optical biosensor from the University of Sydney, Australia in 2017 with a scholarship from the Australian government. Her master's degree and bachelor's degree are both from University Technology Malaysia in Electrical and Electronics Engineering. She's now a senior lecturer at Institute for Research in Molecular Medicine, which is INFORM in short, at University Science Malaysia Health Campus. She has published more than 14 papers in reputed journals and has been awarded national, international, as well as industrial grants. So without further ado, I would like to welcome Dr. Fatin to present her research and her work.
Let me share the slide first. Okay, Assalamualaikum and a very good afternoon, everyone. Thank you, Dr. Yasmin, for the introduction. Let me give a quick introduction again. I am Dr. Fatin Hamimi Mustafa from Inform USM Health Campus. Today, I'm going to story about my research journey of my PhD, as in this is my PhD project about development of a low-cost near-infrared device to monitor nutritional status of newborn infants. These projects involve 3 techniques: simulation, phantom experiment, and also clinical study. So now I would like to bring all of you back to a year of 2012, 2013, when I was starting my PhD. I was approaching my supervisor at that time. Here he is, Professor Dr. Alistair. He mentioned to me politely to do something to develop a device that can be used to monitor nutrition in newborns. And he gave me freedom to choose any method and any technique in this project. And at that time, I was wondering, could I do it? Could I finish it? And my thought was, how to do? What should I do? First thing first that I did was to look at the urgency of nutrition in newborns, and also to look at the definition of newborn of the nutrition. And here it is from the World Health Organization website. Before that, malnutrition includes both undernutrition and also overnutrition. Yeah, according to World Health Organization, malnutrition has become the global burden because it is serious and lasting, not only for individuals and families, but also for communities and countries. And based on the statistics, around 45% of deaths among children under 5 are linked to undernutrition, and this mostly occur in developing countries. Based on this statement, based on this statistic, it shows that undernutrition is very serious, and there is a need for a device to monitor this undernutrition so that fast action can be taken and the number of deaths can be reduced. And it was like a call for me to help these countries, to help these people. So we look at about undernutrition here. Undernutrition occurs when supply of nutrients such as vitamins or minerals are less than energy demand for body to grow, to maintain, and to conduct specific functions, especially related to brain. The worst case, it causes sudden death. Even if these undernourished newborns survive, they are still exposed to long-term health impact, including obesity, hypertension, brain dysfunction, and many, many more. And there are a few indicators to see if this to identify the undernutrition in newborns by observation, to look if this newborn are wasting or stunting, or by measurement to measure their weight, their term of birth, or their length. But then by measurement, but then these newborns, underweight newborn and also preterm newborn, sometimes they are normal. They are not undernutrition, and in some other cases, even though these newborn are normal in normal weight and also full term, they can still in undernutrition category. Therefore, we need a solid indicator to confirm undernutrition in newborns. And there was a study by Carberry in 2013. They found that body fat percentage was the best indicator of nutrition in newborns. These newborns really need sufficient fat in their body, especially during birth, in order to store energy to support brain growth, as insulation to keep warm, and also to fight diseases. Based on this formula, nutrition is closely associated to that body fat percentage here. It gives me an important information that I need to look at what are the existing method, the existing techniques that have been used to measure body fat percentage, because it's related to that undernutrition. This is the first one, a displacement plethysmography, or ADP. ADP is considered as gold standard method, and the body density of a newborn is measured where a newborn is placed on a chamber and inserted into this equipment. From that, body density is measured in terms of mass and volume before and after the newborn inserted into this device. And from that, body fat percentage, fat mass, and fat-free mass are calculated. This method offers several advantages in terms of non-invasive. It is easy to use and it is safe. But then the major limitation is that it doesn't support my purpose of study, because the cost is more than $3,100. So that I rejected this method. Next, we go to another method, imaging. There are a few techniques of imaging, but I named two of them here. The first one is dual energy X-ray absorptiometry, or DEXA. DEXA uses two different energy of X-ray to scan body of the subject, and then from that, body fat percentage, the body water can be determined from the calculation. And similar to magnetic resonance imaging, also based on the scan of the body, but uses magnetic field and also radio waves. These two methods, of course, we can see that very expensive and not in line with my study. And one more thing is that the radiation that used in these two methods are not safe for newborns, especially for frequent scanning. And another method is skin fold thickness. Skin fold thickness is based on measurement of subcutaneous fat and under skin using a clipper. Yes, this method is very, very cheap, because only requires a clipper, but then it suffers from high variability or high standard deviation, because some of the health workers tend to pinch more, some of them tend to pinch less, so that it is not really accurate. So this one also I rejected. Next, we go to hydrostatic weighting. For this method, body density is measured before and after the subject into the water. It based on the principle of achidamis. And yes, this method is cheap, is inexpensive because only require a tank, water, and also a scale. But then, in order to completely submerge newborns underwater, it was a big no for me, and I was not going to do that. So that this method was also rejected. Next, go to another method. Bioelectrical impedance is based on electric flow in the body. With the presence of fat, the resistance and impedance are high. Inversely, for muscle and body water, the electricity flow the electricity flow when uh, encounter these two components, resistance and impedance are high. This method, bioelectrical impedance, are considered relatively low cost. Um, but then, so I put on hold. It seems promising. And next, go to another method, near infrared spectroscopy, based on the measurement using light to measure subcutaneous fat under skin. And from that, body fat percentage can be calculated using equation. So between bioelectrical impedance and also near-infrared spectroscopy, between these two methods, when I proposed to my former supervisor, at first I tend to choose bioelectrical impedance because this is my supervisor's expertise, and so that he can guide me more. But then he mentioned to me that I need to choose whatever I passion on, whatever I comfortable with the field. And at the end, I've chosen near infrared spectroscopy. So let's look at the advantages and limitation of the method that I've chosen. For the advantages, yes, it is relatively low cost, safe, non-invasive, and easily connected to computing devices, so that Internet of Things or IoT can be implemented, and short measurement time, and also do not require skilled operators. However, one of the limitation of the presence of other substances such as water. Now, let's look at if there is any available commercial device in the market that uses a near-infrared spectroscopy technique to measure body fat percentage. And here is the one, Foodtrax. Foodtrax is a commercial device to measure body fat. It has launched a few series that based on targeted population. You can see here /SL estimate for adults population from 18 to 80 years old, A or A/SL for children population from 5 to 17 years old, and the body fat percentage used in this for this commercial device is 84.1 minus 43.6 times R1 minus 156.3 times gender plus 7.8 times weight and etc. Where G is gender, 1 for female and 0 for male, and R1, R2 are near infrared light at a wavelengths of 940 nanometer and 950 nanometer. From this finding, from this commercial device, as we can see that they are not covered for neonates or for newborns. So that it gave me the idea to develop one for newborns, and the body fat percentage uses in this commercial device, showing that it's still dependent on other variables, weight and height, that need extra equipment to measure these two variables, so that the body fat percentage that I was going to develop free from these two variables. Okay. So we look at if there is differences between newborn skin and also adult skin. Yes, based on this table, thickness of skin layers, epidermis, dermis, thickness of stratum corneum, thickness of subcutaneous fat, size of cells and fibers increase with age from premature infant to mature adult. And also, same goes to melanin content, where it's low and medium for premature and full term, and high for that adult. And and the water content in the newborn is 80% compared to 73% for adults. These differences showing that there might be a need for a device that target on newborns. And before that, we look at the principle of near infrared. I know most of you are really familiar with this, but then for those who coming from a non-engineering background, this is an electromagnetic spectrum. Near infrared is an electromagnetic radiation. It lies between infrared region. It lies in infrared region between microwaves and visible, with a range from 700 nanometer to 2500 nanometer. So from this electromagnetic spectrum, there are um, uh, different energies with different applications. And for X-ray and gamma, X-ray and gamma, they possess high energy, but then as I mentioned, that not suitable for monitoring. The radio wave and microwave lowest energy, but the weak signal couldn't penetrate the skin. So that's why infrared become suitable for monitoring. Okay, near infrared applications not only limited to biomedicine, but also in agriculture to measure contents of protein and sugar in foods, and also to check freshness of meats. And also in telecommunication, it has been used to transmit digital data, include telephone and internet through optical fibers. The word spectroscopy means interaction between electromagnetic radiation with a matter. If your study is UV spectroscopy, then it's the interaction between UV light with matter. In this case, the matter is tissue. And here is the skin. In the picture is structure of skin, epidermis on the top, dermis, and then subcutaneous fat. And below the subcutaneous fat layer is muscle layer. And when a light is shined into the skin, there are possible phenomenon occur. Some of the light may reflected, become backscattered light, and some of it experience absorption, and some of the light may scattered in the tissue. So when it becomes a system, near infrared spectroscopy system, it must have at least a light source to emit light into a tissue, and then a receptor to capture escape light from the tissue that carry information about the condition of body that can be manipulated for monitoring or for diseases detection. This is the transmittance type of transmission. If reflectance, the location of receiver is on the same side as the transmitter and captures backscattered light. So absorption in tissue is described in terms of absorption coefficient, showing how much light is absorbed per thickness as the light travels underneath skin. And picture here showing the absorption coefficient of 5 primary substances in tissue, which are melanin, hemoglobin, both oxy and deoxyhemoglobin, water, and also adipose fat. Okay. From the picture, we can see that each substance possess its own unique absorption spectra, where for adipose fat, the absorption peak is at 930 nanometer for here, and for Water is at 970 nanometer. And also we can see that for melanin, it has a really high absorption, so that it might be influenced the near infrared measurement. And for another two is oxy and deoxyhemoglobin. You know that the device that really popular right now, oximeter. The oximeter uses the near infrared technique, near infrared spectroscopy technique, that used to measure oxygen in blood that associated to that COVID-19, right? The principle is actually based on the light measurement to light that used to measure these two components, oxy and deoxyhemoglobin. And we know that oximeter has been clinically verified as the gold standard method. And one more, primary substances not only limited to these 5 substances. It depends on what your method of interest. Let's say if you want to measure protein, if you use this range of wavelength between 750 to 1100 nanometer, you won't get any much information, because the absorption peak or the optimal wavelength of that protein is at 260 nanometer. So that's why choosing the right range of wavelength is very crucial and very important. Next, we look at the another phenomena in tissue, which is light scattering. Two things that contribute to the scattering in tissue. First one is mismatched refractive index, or different refractive index, and another one is size of cells. Okay, when mismatched refractive index is either between different background mediums or between cells and background medium. For example, here, a near infrared light that from the ambient with a refractive index 1 shine into the tissue that possesses background medium that possesses different refractive index. The average is between 1.33 to 1.37, so that scattering occurs there. And then as the light enter the tissue, it bump into a cell, for example, with a different refractive index 1.39 to 1.62, and the scattering occurs again. And we can see that there are changes in directions of the light. Now look at the another degree of scattering light in tissue. That is due to size of cell. Okay, if size of cell is similar to that near infrared light, isotopic scattering or Rayleigh scattering happens. And if the size of cells is larger than the wavelength of near infrared, then it is mid-scattering or forward scattering. And in fact, that near infrared wavelength is from 0.7 to 2.5 micrometer, while the size of particle average is 600 micrometer to 1154.4 micrometer. So it is estimated and expected that mid-scattering occur in the tissue. Now, for scattering in tissue, it is described in terms of absorption coefficient. From the picture, it shows that the two substances, water and adipose fat, scattering coefficient spectra, but then unidentified scattering coefficient of these two made them difficult to separate, unlike absorption coefficient spectra. Okay, and now I've shown you how the scattering they are influenced by that size of cells, and also absorption is influenced by the primary absorbers, melanin, water, and deoxyhemoglobin, and etc. And I also shown that how the size of cells, the size of fibers are different between neonates and also adults, so that it is predicted that, number one, light is predicted to penetrate deeper in premature and full-term skin compared to adult. Number two, because of the size of the cells and fibers are, are smaller than that adult, so that it reduces forward scattering of light. And number three, absorption is more in preterm and full term because they possess 80% water content compared to adult skin, 70%. And also due to lesser melanin content in adult, so that the absorption is more on adult skin. So the light transport in tissue is refers that this modeling refers to radiative transfer theory (RTT) that it's based on the transferred energy light in tissue, and this model has been used in numerical simulation. It is a very long equation and very complex. But what I want to show you here, the important parameters, the important variables that can be used for optimization for testing. So I list down here again the important parameters for testing and optimization that are used in the study. First one is numerical aperture or acceptance angle of detector, acceptance of light. Number two and number three, cover limitation of near infrared spectroscopy, where changes of water, changes of melanin in skin would change the optical properties in terms of scattering coefficient, absorption coefficient, and also refractive index in skin. And number four is a wavelength to optimize, and number five is position angle of transmitter and detector. Okay, for more information, you can refer to this channel. Now, we go to the stage one. Stage one involves simulation and also phantom experiment, with the main objective is to compare performance in terms of sensitivity and optical response between source detector at a position angle of 45 degree and 90 degree, with the objective, that one is main objective. Okay, sub-objective is to test reliability of GAMOS computer simulation in validation with ex vivo phantom experiment. And number two is to define relationship between the infrared intensity with thickness of subcutaneous fat. I wanted to know what is the response of near infrared intensity as the thickness of fat increases. This is the setup for simulation as well as for the experiment. Type of transmission is reflectance, and what the mean of 90 degree is the arrangement of source detector at 90 degree to the surface being measured, and in this case is adipose fat. So a light source, halogen light, is coupled to was coupled to a SMA fiber, and then shine a light into the adipose fat layer with a thickness from 1 millimeter to 15 millimeter in 1 millimeter intervals, and then at the receptor site, a SMA fiber captured the backscattered light and send the information to spectrometer. Similar to that 45 degree angle, the position of the SMA fiber probe were at 45 degree angle to that adipose fat surface. Okay, for sensitivity, there are many sensitivity equation you can use, but I use the simplest one. Summation of near infrared light, near infrared intensity, n plus 1, as n is the thickness of subcutaneous fat, minus reflection, minus n near infrared reflection intensity, and over summation of thickness intervals. And before that, I would like to introduce the software that I use to model light transport in tissue, known as GAMOS. GAMOS is stand for Gen 4 Base Architecture for Medicine-Oriented Simulation. This is an open source software that uses C++ programming language. This software was developed in 2003 for the simulation of passage of particle through matter using Monte Carlo simulation. So in this case, in my study, is the random sampling distribution of optical photons in tissue. Gamma is often used in physics in many areas of applications, including high energy, nuclear, accelerated physics, and many more. And what important to use a simulation is that we can we can study and predict the light in tissue before develop a real near-infrared device, so that optimal wavelengths, effect of different hydration and skin colors on near-infrareds can be investigated. And this is the gamma's application in medical physics. It has been used in imaging, X-ray, MRI, photon computed tomography, and gamma camera. On the right side is for to study particle transport in medical equipment, showing here that various lines represent different particles or different energy, such as photon, gamma, electron, etc. Okay, back to my simulation. So I developed a virtual subcutaneous fat layer, various thickness as mentioned, and then assigned optical properties into tissue, optical properties as mentioned, derivative index, scattering coefficient, and absorption coefficient, and then developed a virtual source and a virtual detector, and the parameters of those source detector were similar that with that used in the experiment, and then 10 to the power of 8, 10 to the power of 8 of optical photons were launched into the tissue, and the virtual detector recorded the number of optical photons. And on the right side, showing to the view of traces of optical photons path during simulation. Okay, for ex vivo phantom experiment, I firstly prepared BFAT layer, actually ground BFAT layer. I the BFAT I blended and then put it on the inside the casing with the diameter of 15 centimeter, and then set up the experiment as I mentioned just now, and then uh, do the measurement for 3 times at three different locations, and then record optical response. Results for stage 1. The first one is to see whether the simulation is reliable with that experiment. We can see here that the simulation and experiment of the graph showing that the logarithmic over the thickness of the subcutaneous fat, showing that they are in agreement. They are in an agreement. At first the intensity increase at the lower thickness, and then at a certain point it becomes saturated, and with no longer change in intensity with increases of thickness. And also showing here that high sensitivity of near infrared light at lower thickness may be maybe show that this is the promising method for undernutrition detection. And to compare between 45-degree and 90-degree arrangement, firstly is to see the intensity of near infrared light higher for 45-degree compared to 90-degree for both simulation and also experiment. And for calculated sensitivity, the sensitivities at 45-degree position angle are higher compared than 90-degree position angle. Okay, because of the simulation is valid for body fat measurement, so that for stage 2 only simulation, for first and second objectives to study the effect of varying melanin and water respectively, and this is the limitations of an infrared. And number 3 is to define optimal wavelengths for the development of a near infrared body fat device. For methodology, so perform using GAMOS, and then I developed two single subcutaneous fat layer with different hydration. First one is normal hydration, second one is dehydrated skin layer, and also develop four skin models using four skin models. That skin model one is Caucasian with normal hydration. Skin model 2 is Caucasian with dehydrated. And for skin model 3 and 4 is African skin with normal hydration and dehydrated respectively. And then assigned optical properties into each layer and developed a virtual light source and detector. Okay, for absorption coefficient, I used this equation, absorption coefficient for each layer equal to this equation, and from the table 1, volume fraction is actually the proportion, the percentage of component in that in the respective layer, and for volume fraction of water, we can see here that for Caucasian dermis, epidermis and dermis, the V water is 0.6 for normal hydration, and for dehydrated is 0.1. And the difference of in terms of skin color, the difference in terms of V melanin 0.0010 for Caucasian, and higher for African 0.03. Note that intrinsic is other component than those 5 substances. Okay. For scattering coefficient, this equation was used where it shows that it highly dependent on wavelength, with A and B are constant based on this table. And then refractive index, we know that refractive index has direct relationship with that scattering coefficient. Therefore, if one of them changes due to varied melanin or water, the other parameter was assumed to change equally. Based on the past study showing that increased water, the increasing of water decreased the refractive index value by 5%. And the simulation diagram showing for simulation, showing that the arrangement of source and detector is they are at 45 degree to the skin, to the layer, similar as what been set up in the past study. And then the picture below showing 2D view of the traces of photon path during simulation in GAMOS, and near infrared was defined by number of recorded photons over number of launched photons in percentage. Results for stage 2, it obviously are seen that the variation of hydration is minimal at 2 ranges of wavelengths. First one is 890 to 940 nanometer, and the second one is 1010 to 1100 nanometer for both single layer and also complete skin. And skin color, yes, it has significant effect on near infrared spectra because light was absorbed more in African skin than Caucasian skin due to the presence of greater melanin constituent in African skin. So that these two ranges of wavelength suggest that this wavelength considered for the use in measurement of body fat to solve the variation of hydration in neonates. And the stronger influence of skin color in near infrared shows that the melanin effect need to be corrected either by independent measurement, measure color space LAB, or by a modeling approach. This include adjustment or correction in body fat percentage equation model. For further reading, you can refer to this thing. Okay. Now, next we go to the important stage, clinical study. The objectives is to test and the effect of the use of optical component with higher numerical aperture or larger acceptance angle, and then to develop a statistical model to estimate body fat percentage in newborns from near infrared reflectance measurement based on body fat percentage from the gold standard ADP measurement. For the first thing that I did, data collection, the measurements were taken at hospital, Royal Prince Alfred Hospital, Sydney, between September 2015 to December 2015 on 16 units within 48 hours of birth. And the measurements were conducted in 3 times on the skin surface of both anterior and medial thigh while breastfeeding to avoid movement from the babies. And ethics was approved by Human Research Ethics Committee, and all devices were found to meet medical safety regulations. So, I divided into 2 cohorts. First cohort is measurement with cosine corrector or with a larger numerical aperture, and cohort 2 without using cosine corrector. And this is the measurement setup, similar with that in phantom experiment. The difference is that I add cosine corrector there for cohort 1 with cosine corrector, for cohort 2 without that cosine corrector. And on the same units, body fat percentage and weight were recorded by ADP per standard measurement system. This picture are the emulations of near infrared measurements on anterior and medial thigh, because to get the measurement on real newborns, they need consent from parents, so cannot be shown here. And number 3 is statistical model development. Use ratio at 2 different wavelengths in order to remove and normalize the baseline offset or noises, and then to reduce effect of hydration, use those 2 different range, using those 2 ranges of wavelength optimal that I found in simulation. And then because of skin color affect the infrared measurement, so only selected subject with white skin category. And then MATLAB software was used to apply linear piecewise interpolation, and then use an ordinary least square linear regression model to define body fat percentage that correlate with ADP method. And for results and discussion, I developed a body fat percentage equation that can see that the A1, 2, 3, 4, and 5 are the variables, are the constant variables that you can see in the table on the left side. R1 is a ratio of 890 over 1020 nanometer, R2 920 nanometer over 1010 nanometer, R3 is the ratio of 1010 over 900 nanometer, and G is the sex or the gender that's assigned, 1 for male and 0 for female. And we can see from this body fat percentage, it is free from other variables that need extra measurement devices. And from the results on the table on the right side, the value of R, the value of correlation coefficient, are higher for cohort 1 compared to cohort 2, and the value of RMSE, root mean square error, and p-value are lower for cohort 1 compared to cohort 2. The linearity is valid if through the residual plot. We can see that the data here randomly distributed over the axis, and Also, on the right side that showing linear regression lines of near infrared body fat percentage over ADP body fat percentage. And however, number of samples need to be added to confirm this linearity. As a conclusion, the improvement offered by the cosine corrector in the near-infrared body fat measurement is demonstrated the importance of appropriate equipment and device selection in near-infrared configurations, and this shows the potential of direct and low-cost LED-based near-infrared device. That maybe 5 LEDs could be allocated around a cosine corrector that couples to a wavelength range detector and filters. For more information and more results, you can refer to this journal. And for comparison, I recall again, for comparison between ADP and infrared spectroscopy, ADP, the gold standard cost is more than $300,000, and near infrared spectroscopy system that used in study, the cost is more than $10,000. And for this device that I developed, the prototype one uses 5 LEDs at 5 different wavelengths and covered with 3D printed mold, and the cost can be $1. Okay. And of course, this is not an individual work without my research team. Firstly, to my former supervisor, Professor Dr. Alista, thank you for believing in me and support. And then Professor Dr. Hita Jeffrey, she is clinical academic neonatologist for the advice in terms of neonates. And then Dr. Peter Jones, he is a postdoctoral researcher for bombing me. Thank you for bombing me critical questions. And also thanks to Mrs. Emily, she used to be a research assistant. Thank you for helping me in documentation of ethics, and also helping me to talk to parents to get consent from them. And last but not least, thank you to the funder, the Bill and Melinda Gates Foundation, for the funding support. And before I end, I would like to thank for all of you to join and listening my talk. And for any further question, you can directly email to me. And also, I warmly open for collaborations. Thank you. That's all.
All right, thank you very much, Dr. Fatin, for the impressive presentation. I would just like to remind the audience, if you have not filled in the attendance form, please do so. You may find the link in the chat box. Also, if you have any questions for Dr. Fatin, you may type in there as well, and we will address them. So, okay, so far no questions in the chat box.
Assalamualaikum.
Okay. Waalaikumsalam, Dr. Fairuz.
Dr. Fatin, terima kasih. Fantastic talk. Satu soalan, satu ke dua? Satu mungkin lah. Satu soalan. Ada apa continuation from the work that you done dekat sini? Ada sambung?
Continuation. Yes, it has been continued by other students, where they go to South African and India for measurement on darker skin of newborns. But then I think it's still ongoing, but now on hold because of COVID.
What about here?
Here, not at the moment.
Okay. On that note, on the darker skin, because of course lah, kalau kita pakai IR punya style ni, memang warna kulit tu memang mempengaruhi sangat besar. Ada future plan ataupun ideas on how to sort of make it autonomous, meaning the sensor will sort of recalibrate itself to determine the color of the skin before it goes into ambil correlation numbers and point. There's a lot of correlation kan, dia punya coefficient A1, A2, A3 tadi tu. Is there any work towards there now?
At the moment, no lah.
Oh, okay. I think
If you have any idea,
perhaps
I will.
that can be something to look at kot, sebab if you have a lot of sample kan, macam dah ada banyak data dari Africa, India and whatnot, so probably prior to measurement, prior to reading, the system can auto calibrate to select which coefficient to use to calculate the body fat percentage tu.
Oh,
I don't know, that's just an idea.
interesting.
Okay,
I
good.
juga.
I hope you can start ni apa sambung benda tu kat Malaysia, get the apa tu norm for Malaysian skin lah.
Actually I ada approach lah sebab I kerja kat hospital kan, so I ada
Yes.
doctor from ni lah department, maybe the department, and then dia pun interested lah, so actually ada plan jugalah untuk continue.
Good. You should. Good.
For skin this ni lah dekat skin kita kan, skin not really dark, not really fair kan.
Yeah, we have a nak kata brown tu tak ada juga kan. Quite apa unique color kan.
Yes,
Nice.
yes.
Good job. Thank you.
Thank you.
Thank you, Dr. Fairuz. Any more questions from the floor? Okay, like I would always see people getting Bill and Melinda Gates punya grant kan, and for you to be part of that is amazing lah, Dr. Fatin. Were you okay? I mean, this may be irrelevant, but were you part of the process where they wanted to propose the research for the grant? Were you from the beginning, the starting of the study?
From the beginning. But then when I enrolled my PhD, my supervisor already got the grant. It just started.
I see. That's amazing. Okay. I have another question. You did mention just now that there's another method that you were interested in, right? Bioimpedance.
Yes.
I think that's what it's being used dekat our weighing scale yang boleh baca body fat, right? Yeah. So comparing that to NIR spectroscopy, yeah. Has it been tested for neonates, bioimpedance, and how is NIR better than bioimpedance?
Actually, I didn't check that for neonates because I straight away go to near infrared spectroscopy because that my passion on optics.
I see.
Yeah. So I have no idea, honestly.
So like in your experience, why would you think NIR spectroscopy would be the way to go compared to bioimpedance?
Because actually when I went to the hospital, I saw that oximeter has been they used oximeter to measure that oxygen for newborns, and then when I saw that one also using near infrared spectroscopy technique, so why not using this similar technique for my project? So that I quite confident with that technique.
Okay. All right. Any more questions? Someone said bioimpedance could be difficult for baby. Oh.
Okay, thank you.
That's something to consider.
Investigate that.
Oh, in terms of testing, I'm guessing the location where you take the body fat percentage would matter as well, right? Or it's just the same?
Just choose on type skin.
Oh no, I mean like okay, tapi like kalau compare it to ambil dekat tangan ke dekat other parts of the body.
One of the I know the issue is for adults, sometimes different part of body they tend to have more fat compared to other parts, but for newborns not, it's distributed evenly with the fat. Yeah.
Oh, that's interesting. Okay, so it seems that we don't have any questions from the floor. I guess we will wrap it up in that sense. So before we end it, I would like to once again thank Dr. Fatin for sparing some time with us and for sharing this very interesting research of hers. And before we go, I would like to take a group photo. So I hope that everyone can turn on your videos so that we can take a photo together. Okay, still waiting for all of you to turn on your videos. Okay. Okay, so I'm gonna count to 3. 1, give your best smile. 1, 2, 3. Awesome. Okay, just give me 1 second.
Dr. Fairuz, kenapa hijau sangat belakang?
Green screen. It's a green screen. Virtual green screen.
Okay, all right, everyone. Thank you again for joining us.
Thank
I hope to
you.
see you
Thank you very
guys
much,
next
everybody.
month.
Bye.
Good job,
Bye.
Dr. Fatin.
Okay,
Good job.
thank you.
Thank you.
Bye.
Thank you, Doctor. Thank you, Doctor.